All right, in our final lesson, we'll be looking at the present value of annuities. Now, remember that in an annuity, we make regular payments. When we're talking about present value, though, it's going to be a little bit different. Now, let's say you want to invest a sum of money that will provide you with a payment of $5,000 each year for 5 years during university. So you're going to invest a large amount, and you want to be able to pull out $5,000 each year. Now, I've already kind of drawn out the timeline here. So in years 1, 2, 3, 4, and 5, you need $5,000. Now, on the face value, you might think, okay, well, I need $25,000 then. But that's not actually the case because you're earning interest of 4% compounded annually all the way through. Now, it's compounded annually right now, so I don't have to divide that 4%. But we have to think, how much money do we need in our account at the very beginning in order to take out $5,000 each time? Now, here's what you have to think of, and you're going to have to think back to our lesson on present value for compound interest. This $5,000 in year 1, it's not actually worth $5,000 at the very beginning. Because whatever amount of money we have at the beginning, it's earning interests. This $5,000 is only $5,000 because it has earned interest. So what has actually happened, because it has earned interest for 1 year, 5,000 divided by 1.04 gives us the present value at the very beginning of what that was worth. So if I calculate that, it's only about $4,800 at the very beginning, but $5,000 after 1 year. Now, the payment in year number 2, same sort of idea, but it's earned interest for a longer amount of time. It's earned interest for 2 years. So 5,000 divided by 1.04 squared. So that $5,000 was actually worth even less at the very beginning because it was able to grow for 2 years. Now, if we continue this, well, each of these years going forward, each of these payments has 1 additional year where it's allowed to earn interest, all the way until we get to the end where year number 5, that payment has actually earned interest for 5 years in total. So if you take a look at this again, it's again going to form a geometric series. Now the difference here from the last lesson, we did have a first term of r in our geometric series, but that's not the case because if you take a look at all of these payments, none of them are actually worth only $5,000 in the present. So when we're figuring out our sum, and now this is in general, so I'm not going to be using these numbers anymore. The very first term in our sequence or series is r times 1 plus I to the power of negative 1. Because it's able to earn interest for 1 year or 1 month, whatever it is. The next payment is worth r times 1 plus I to the power of negative 2 because it's able to earn for 2. Now, if we continue on going, if you take a look at the final payment that's being made, so in this case in year number 5, it was able to earn interest for the same number of years, which is 5. So the very last payment that is made is r times 1 plus I to the power of negative n. So if I'm putting together my geometric series, here's what it's going to look like. Now, the first term, a, is actually r times 1 plus I to the power of negative 1. Okay, that's our first term right there. Now, what is it increasing by? What is the common ratio? Well, if you take a look at it, the r value, the exponent is getting smaller each time on 1 plus I. So the common ratio is actually 1 plus I to the power of negative 1. That's what we're multiplying by each time to go down our series. So now I can put together the equation. So the sum of the first n terms. Now I'm going to save us some time here. I'm not going to write the sum. I'm going to write PV for present value. Now the a value is r times 1 plus I to the power of negative 1. Now that's multiplied by, the common ratio is 1 plus I to the power of negative 1. Now that's going to have an exponent of n. Now I'm going to save us a bit of time here. We know if an exponent has an exponent, we multiply them. So I'll simply write this as 1 plus I to the power of negative n. Now that will be subtracted, or 1 will be subtracted from it, and we divide the whole thing here by the r value, 1 plus I to the power of negative 1, and then subtract 1. Now, we are going to simplify this a little bit. It involves a little bit of trickery. Now, just remember, as I told you in class, you don't have to be able to put these equations together, but I do want to show you where they come from. It's not like some sort of voodoo magic. Now, what my trick is going to be to simplify this, we know from our previous work that if we multiply the numerator and denominator by the same thing, then the actual equation or expression is not changed. So if I multiply by 2 over 2, I might be able to simplify it, but I'm not actually changing what the numerator and denominator is. Now, what the trick is going to be, I'm going to be multiplying by 1 plus I over 1 plus I. Now, why that is exactly, if you take a look at the numerator, now we have this set of brackets multiplying r times 1 plus I to the power of negative 1. What the 1 plus I is going to do is it's going to cancel out the 1 plus I to the power of negative 1. Because this means that we are dividing by 1 plus I to the power of negative 1. So those two will kind of cancel out. Now, I am going to have to expand, though, the 1 plus I when it multiplies in the denominator. So our present value is now, let me stick with one color only. So our present value is, we got r, and then 1 plus I to the power of negative n, subtract 1. Now, when I expand the denominator, both 1 plus I to the power of negative 1 and negative 1 have to be multiplied by 1 plus I. But as we just suggested in the numerator, this and this will kind of cancel each other out. So we're left with 1 and then subtract. Now 1 times 1 plus I is 1 plus I. Now, just like in the last lesson, though, I can simplify the denominator there a little bit. So 1 subtract 1 is 0, it's gone. But what I'm actually going to have here is negative I in the denominator. Now, typically, we don't want to have negatives in the denominator. So this formula here would actually work, but we want to simplify this a little bit. So we want to transfer that negative sign into the numerator. Now, we're not going to apply it to the r. We're actually going to apply it to the brackets right here. And if we apply that negative, basically both of them will have the opposite sign. So instead of negative 1, I'm going to have 1, and then I'm going to subtract 1 plus I to the power of negative n. So this right here is our formula for the present value of an annuity, and it'll tell us how much money we have to invest in order to have a certain regular payment over time. So an example of what this may look like, your grandparents leave you enough money to get a semi-annual payment, so that's twice per year, of $5,000 for 25 years. How much do they invest at 2% compounded semi-annually? So they're going to invest a very large sum of money, and you're going to be able to withdraw, so your R value, you're going to be able to withdraw $5,000 twice per year. Now the interest rate, as usual, is 0.02 divided by 2. So 0.01. Now the n value, 25 years are going by, but we're compounding semi-annually and our payments are semi-annual. So n is equal to 50. There's going to be 50 times that you're earning interest and making payments. So putting together the formula, so we got $5,000, and then 1 minus 1 plus I is 1.01 to the power of negative 50. And that's all divided by I, which is 0.01. So we can just type this into our calculators and we get a present value of $195,980.59 approximately. So that's how much money they'd have to leave you in order for you to withdraw $5,000 twice a year for 25 years. Now, the final question here will be like the final question in the last lesson. So if you borrow $100,000 to buy an RV, the bank will charge you 6% interest compounded monthly. Now, usually when you borrow money for a car, for a house, or something like that, you're charged interest, but you're able to make regular payments. So you pay down your debt little by little until you reach the very end. So you borrow $100,000, this is actually your present value because that's how much the money is worth right now. The bank is charging you 6% compounded monthly, so 0.06 divided by 12, 0.005. And the payments are being made over 10 years. So 10 years times 12, because it's monthly, is 120. So what we don't know here, we don't know how much our payment is. We don't know R. So same sort of idea as before. We substitute in whatever we know. So $100,000. And I'm just going to substitute in all the information that I know according to where it goes. And now I just have to solve for R. Now, I've already solved this here by pausing the video because the solution is very much similar to what we had in the last lesson. So I've multiplied the 100,000 by 0.005 to give me 500. And now I divide by 1 minus 1.005 to the power of negative 120 on both sides. And this is what the regular payment would have to be, $1,110.21 approximately. Now this question here is also asking how much interest were you charged? So obviously if you're borrowing $100,000 to buy something, you're going to be paying back a lot more than that because you're being charged interest as you go. So here's what I'm going to do. To figure out how much interest we were charged, well, I'm first going to figure out how much did I actually pay in terms of my payments, because that amount's going to be larger. Now, we just figured out the payment to be $1,110.21. But how many times do we make that payment? Well, remember, it was monthly for 10 years, so that payment was made 120 times. So I can calculate that, and by subtracting what I originally borrowed, that will give me the difference in how much interest was actually charged. So in this case, we were charged interest of $33,225.20. So quite a lot of interest, and that's what's going to happen if you're charged interest over a long period of time for such a high amount. You will be charged a lot of interest.